So do you feel a need to go through that quiz? Would you like to go through it or no? No one, see, the answer shouldn't take us too long. All right, so on the first one, you're asked to find y prime, so you have to recognize you have a product rule here, right? Right there. So if you have a product, you are going to take the derivative of the first function, right, which is 2x, and then just times the second function, arc sine of 3x, and then plus, now the derivative of arc sine of 3x, which would be 1 over the square root of 1 minus the argument squared. So it would have to be 3x squared here, which would be 9x squared. And you're not done with this arc sine yet. Now you need to take derivative of the argument, which is 3. And then you finish off the product rule with x squared there. Does that make sense? Okay, so we can move the 3x squared up on top, and that would be pretty much done. Okay, this one, we have no product, we have a chain rule. So to take derivative here, we have to take the derivative of arctangent of something. And what is the derivative of arctangent of something? 1 over 1 plus whatever the argument is, right, squared. So you're going to be doing square root of x, but then squared. So that's really going to be an x. And then we're done with the derivative of arctan, but now we need to go inside, take derivative of this, which is 1 over 2 square root of x, or 1/2 x to the negative 1/2, however you write it.
Do you want to FOIL after that? For the denominator?
No, you don't need to. You can just leave it. If you did, it's fine. But okay, that's it. Okay, so all right, now we proceed in the class, right? We're moving on to antiderivatives now. So there's still probably going to be some overlap from Cal 1. So many of you have probably seen some of this, which is great, because the new stuff will come, and you'll be kind of wishing we were back talking about the old stuff. All right, so antiderivatives. How many of you saw antiderivatives in Cal 1? All right, so we have a basic understanding. I'm going to treat it like you've never seen it, all right? So a function, capital F, is called the antiderivative of little f on the interval I if the derivative of capital F is equal to little f for all x that live in the interval. So all this is saying is, let's say we have a scalar function, or not a scalar function, it is a scalar function, but let's just say we have a function like 2x, all right? An antiderivative of that is any function, capital F of x, so that when I take the derivative of this, I get that. So what is an example of an antiderivative of that? X squared, right? X squared would work. Is that the only example? Can someone give me another one? So I'll call this f sub 1, because I'm going to call this one f sub 2. Is there another function that if you take the derivative of it, you get this?
X squared plus 1.
X squared plus 1. Because having a constant out here doesn't change the fact that the derivative of this is 2x, right? Can we come up with another one? X squared plus any number you want, right? So I can say plus 4. I can say plus 10, minus 4, minus 3, plus pi, minus pi, right? Any number I could ever come up with, the derivative of all of these would still be 2x. Agreed? So this is an antiderivative, okay? It is an antiderivative of that. This is an antiderivative of that. This is an antiderivative of that. So if somebody gives you a function and asks you to find an antiderivative, there should be an infinite number of answers, shouldn't there? But they will all have the same property. They all have to have the x squared in there, right? And then the number here, all that does is it just takes that picture and just moves it up or down, right? So if capital F is an antiderivative of little f, then capital F of x plus any constant is the most general antiderivative of little f. So if we write capital F of x equals x squared plus any constant, this right here would be called the general antiderivative of 2x. Okay? Now, here's that example that I just showed you in pictures. So we want to try and understand what this actually means. So if we look at this red function, this is the function 2x, right, which is a line. Agreed? So capital F of x right now is this blue one, is just the x squared function. We know that the derivative of this is equal to this, right? But geometrically what this means is that if you go to any point, let's say I go to this point right here, this is 3. If I go up here to this blue function and I take the derivative there, what would that give me? Like what would that value represent? The derivative of that function at 3 would be geometrically the what of that function? The slope of the tangent line. So there's like a little tangent line on that function, right? And the slope of that tangent line, right, is actually the value of this function at 3. So if I go and I plug 3 in here and I come over, where would I be? It's 6, right? So the slope of the tangent line right here is 6. Is everyone making that connection? The slope of this line is the value of the red function at that point. Yes or no? So let me go to another point. Let's go to -2 over here. If I go to -2 and I plug in here and I want to know the slope of that line, what is the slope of that line? How can you find it? Go to -2 on this blue function, tell me the slope of that line. What is it?
Take the derivative of the function and then plug in -2.
Yeah, so you take the derivative of the function, which is 2x, and you would plug in -2, which really means, here's 2x, right? There's the graph. So plug -2 into this function, and you get -4, right? So why is it that, this is just one of the antiderivatives, right? Why is it that any of these should give you the same answer? Like, you take any of these, you take their derivatives, you get this. Geometrically, doesn't that mean that all of those curves, every one of these, right, all these parabolas moved up and down, all have the same property? Like if I move to some point here, there we go, right there. Do y'all see that? If I go to any curve, any of these curves in this family, okay, any of them, and I go to some x value, well, I'll go here, and I go up to any of them, right, straight up. Do you see that the slope of the tangent line is the same for all of those? They all have the same slope, which is represented by the fact that they all have the same derivative. So moving the function up and down has no impact on the slope of the tangent line at a given point. So if you're going to take anything away from this, remember that given a function, the antiderivative creates a family of functions that all have the same shape, just moved up and down. That's it. All right? So here's another example. This one I'm just going to give you the picture, and we'll talk about how we get the antiderivative later. But this is just to illustrate again. If somebody gives us some function, we go find the antiderivative, right? Here's the antiderivative. It creates this blue one. There's a family of functions. All of these functions right here are the same in the sense that the shape is identical. The slopes of the tangent lines at any given x value is the same. They're just moved up and down, which has no impact on the slope, right? So our goal is going to be for the next couple of weeks is to be able to find the antiderivative of a function. If somebody gives you a function, you need to be able to find its antiderivative. And then after that, we'll talk about what we can do with it, all right? But we're going to focus all of our attention on, I give you a function, you give me that, all right? So going from here to here, we're going to go backwards. And in the beginning, it's actually not that hard to do. I think most of you would agree with that once we look at these notes. We already know a lot of them. We already know a lot about antiderivatives because in Cal 1, we know the derivatives of a lot of things, right? So let's go through these kind of, I'm gonna do it on a different page. So let's talk about the things that we do know. All right, so what we know from Cal 1 is that, let's say we had the sine function, sine x. Do we know its derivative? It's cosine x, right? Okay, so using that information, we could say that if we're given our little f of x to be cosine x, then what would the general antiderivative of that be?
Sorry.
Just sine x, right?
Yeah.
Sine x plus some constant. So again, the idea is that I already know that the derivative of this gives me this, so if I want the antiderivative of that, it should be that, right? Plus some constant. And we could do this for everything we already know. So what's another one we know? We know the derivative of cosine of x, right? What's that? Negative sine of x, right? So if we're given, let's say we're given our little function is not cosine. What if we're given our function is sine x? So that's not quite this, is it? What we could do is multiply both sides of this by -1, right? And so the general antiderivative of this would be what? Negative cosine x plus c. And the good news about antiderivatives is you can always check your answer, so long as you can take a derivative, right? So like if I want to check, is this the antiderivative? Just take the derivative and you better get that, right? Take the derivative of this, you better get this, right? So derivative cosine of x is negative sine of x, but then make it negative again, so that's going to make it positive, so we're there, right? What's the next trig function that we know the derivative of? Tangent, right? So we know derivative of tangent x, we know is secant squared x, right? So if someone were to give us a little function, little f, is secant squared x, then the general antiderivative of this would be what? Tangent of x plus c, right? And we can do this for all 6 trig functions, right? Go backwards. But let me ask you this. What if we're given that our little scalar function is tangent x? Then what is capital F of x? So when we were in Cal 1, did we ever have something that when we took the derivative we got tangent? Just tangent.
It's sine over cosine, isn't it?
Was it?
Oh, no, that's not.
No, sine over cosine is tangent. I'm saying, did we ever have something here in Cal 1 that when we took the derivative we got tangent x? I mean, we know the derivative of tangent is secant squared, but that's not what we're asking. We're saying, is there a function over here that when you take its derivative you get tangent? We did not have anything like that, did we? Agreed? So this is an open question. We don't know the antiderivative of tangent x yet. Okay, so what I'm trying to illustrate here is that there are many things you do know from Cal 1 already, right? Antiderivative-wise, but there are things that you don't know. What would be another one in terms of trig stuff that we do know? How do you mean? If we're given, you have to give me something that you know the derivative, you know, over there. Cosecant. Okay, so you're telling me that in Cal 1 the derivative of cosecant x was negative cosecant x cotangent x. So the only thing I can say here is that if I'm given negative cosecant x cotangent x, then yes, the general antiderivative of this would be cosecant x plus c, right? Because the derivative of this is this. Yeah? Are y'all following me? Y'all are like, how about this? What if I give you this? Do you know its antiderivative? Well, go look on your chart. There's nothing there in Cal 1 that you took the derivative of and got this as your answer. The derivative of negative cotangent x would be positive cosecant squared x.
Oh.
Right, with the squared on it, right? So it doesn't, now if this were squared, yes, we would be able to go backwards. Right, you see that? Okay, so this is kind of the trig stuff that we should be familiar with. Let's talk about some non-trig stuff. So I'm going to continue this idea. I'm going to give you a little function, a little f, and you're going to try and come up with a capital F. So what about this one? This one should be an easy one. Why is that easy?
It's the same thing.
Because the derivative of that was itself, right? So if capital F of x here would be itself plus c, right? Take the derivative of e to the x plus any constant, and you would get back e to the x. So we're in business there. The derivative of e to the x is e to the x. The antiderivative of e to the x is e to the x. It's like the best case scenario. All right, let's do another one. What's something else we know? I'm going to do this one on purpose to try and confuse you. Do we know this? Well, the derivative of, okay, so the derivative of natural log of x is 1 over x, right? The derivative of it. So the antiderivative of this, is it 1 over x? That means if I take the derivative of this, do I get this? No. Take derivative of that, I get this, but that's not what we want. We want derivative of this gives you this. So in Cal 1, did we ever take the derivative of anything and get natural log of x? No, we didn't. So this is an open question. We will attack that later. We're not ready for it. We're not ready for a couple of these. I'm just trying to illustrate. There's some things we know, there's some things we don't. Okay? But the things we know, you need to know. Like, everything from Cal 1 needs to come over with you. All right? So let's use this. There is something I can take from this. I learned something here. If little f of x is what? I can go backwards. If little f of x is 1 over x, well then I can say capital F of x is natural log of, we usually put absolute value of x plus c. Now, do you agree with that? We only do the absolute value because domain restrictions on log. We need to keep the argument positive, so put absolute value to guarantee that it's going to be a positive, that it's defined. So if I take natural log of x, I take its derivative, I should get 1 over x. Adding a constant changes nothing. So that one we know, right? Anything else that we might be able to bring over? All the trig stuff, right?
Question.
Yes.
Let's say we had like a 4 over x. Would it just be 4 ln
Yep,
x?
it would be 4 ln x. Yep. And that you can kind of answer if you think about it. If this were a 4, right, you're asking then would it be a 4 out here? Well, when we take derivatives, when we have constants in front like this, they just come along for the ride, don't they? So I can ignore the 4, take the derivative of natural log of x, get 1 over x, and then multiply it by 4, and that will give me 4 over x. So it'll come with us. All right, let me give you another one. If little f of x is that, then what would capital F of x be? Arctangent, tangent inverse of x. Now, how do you know that? Because we just went over that last week, okay? And I said, remember this one, right? If you ever see 1 over 1 plus x squared, right, you need to realize that is the derivative of arctangent. So the antiderivative of that is this plus some constant. And we could do that for all those arc trig functions we know, right? Let's do another one. If little f of x was 1 over the square root of 1 minus x squared, then the antiderivative of that would be arc sine x plus a constant, right? And that would work for all the different inverse trig functions and all the hyperbolic inverses. So in theory, we have ways to go from a function backwards, right? So long as it fits perfectly into our little box of formulas. All right, let's move on to something else. We started with 2x. That was the first problem we did, and everyone went backwards, right? Everyone went from 2x, everyone went backwards to x squared plus c. No one seemed to gripe about that at all. Everyone seemed happy with that. How about this? Can we find the general antiderivative of this? Well, remember with derivatives, you can do term by term. Right? When you take a derivative, you have addition and subtraction, you do them term by term. Well, when you're doing antiderivatives, if you have addition and subtraction, you can look at them term by term. So the question would become, can we find an antiderivative of this, an antiderivative of this, and then an antiderivative of this? Okay, so let's discuss how we would find the antiderivative of those. So how about the x cubed? What's the antiderivative of x cubed?
2x, 3x.
That's the derivative. It's not what we're talking about. X to the fourth over 4. What the heck? X to the fourth over 4. I'm going to write it a different way. X. Why does that work? Why does that work? That's clever.
Because when you bring down the 4 to the front, it'll cancel out and you lose to 1 because you x cubed.
Yeah, so what we want is to take the derivative of something, right? And that we know that when we take derivatives of power functions, we subtract 1, right, from the power. So we know that if we need to wind up at 3, then this needs to be a 4, right? But the problem with that is if we just did x to the fourth, when we take the derivative, the 4 would come out, and we don't have a 4 here. So we put a 1/4 in front, right? And that'll basically wipe the 4 out when we take the derivative, and then we get back the x cubed. Now, I'm going to give you a general formula for this, but I want us to see it before we actually put a formula on the board. What about the next piece? Someone else?
2x squared?
2x squared. So I'm going to do it slightly different. I'm going to get to the same answer. I'm going to ignore the 4 for now. And the reason I'm going to ignore the 4 is what we just talked about with the natural log. The 4 can just come with us, right? The 4 is here in our answer. Let's just look at x. What's the antiderivative of x? So we know we need an x squared, right? So we need x squared. But the problem is when that 2 comes out, right? We don't want it there because we need to turn it into x. So what do we put out in front of this? A half. And that will wind up being 2x squared. And then what about the last piece? What's the antiderivative of 1? Just x. You just need to remember that derivative of x is 1, right? With respect to x. So, and I'm missing one more thing. Always have to throw my plus c out here. All right, so this leads us to a rule. And this is our first rule when it comes to antiderivatives. It's called the power rule. For antiderivatives. Not for derivatives, but for antiderivatives. Here's what it says. If little f of x is x raised to any power, then the antiderivative of this should be. So what do we know about the power of the antiderivative? The power of the antiderivative has to be 1 more than that, right? So like over there it was cubed, the antiderivative had to be to the 4th. Here it was to the first power, the antiderivative had to be squared. So if the power is n, then the antiderivative has to have an n plus 1 power. However, because we know that when we take the derivative of this, that power is going to come out, we don't want that power out there, right? So what we do is we divide by the power. So in front of this we write 1 over n plus 1. Now some people learn this formula this way. It's the same formula, okay? It's the same thing. I just always like to put it out front because we know that taking derivatives, the number being out front is nice and convenient because the power comes out and It's just all the numbers are out front and you can manipulate them.
So x to the n plus 1, right?
Pardon?
Isn't that right there?
Oh, I forgot to put, yes, thank you, n plus 1, sorry. So, but I'm missing one other thing. Plus c, okay. So this is your power rule for antiderivatives. So let's use that. How about this one? I forgot to mention something. This formula, let me erase this. This formula does not work one time and one time only. This formula is only good so long as n is not -1. Because what happens if n is -1? Look at your formula. If n is -1, what is this?
0.
That's 0. 1 over 0 is undefined, right? So this formula breaks down when n is -1. Agree? But that's okay, because what if n was -1? If n is -1, then what's the function we're looking at? It's x to the -1, which is 1 over x. And didn't we already talk about what the antiderivative of this is? It's natural log of x, right? So we have all bases covered. When it comes to x to any power, we've got a formula for it, with the exception of when it's -1, but that's just 1 over x, and we know the antiderivative. So every power of x we ever see, we should be able to find the antiderivative. And the next example will illustrate that. Are you all following me? Okay. So let's try and find capital F of x here. And I think it's stick time. Maybe. Where are they? Oh, there they are, hiding. It's not cooperating. Jordan. Where's Jordan? How's it going, Jordan? All right, so Jordan, little advice to you first. When you see constants, just bring them down, all right? So I'm going to bring this constant down. Now, that means all I need is for you to discuss with me how you're going to find the antiderivative of that. So how would you approach that? Can you even use this? Okay. You just need to know what the power is, right? So what's the power on that one? 1/2. So this is really x to the half. So n is 1/2, right? So then what would this antiderivative look like if we use this formula?
It'd be 3 times 1 over 3 half.
1 over, I want you to go even slower. So
3 times 1 half, or 1 over 1 half.
1 over 1/2 plus 1. So that's your 1 over n plus 1. X to the
1 half.
1/2 plus 1. All right? So that right there is this formula being performed on just that piece right there. Okay? You want to keep going? Okay, so this one right here, I'm going to drop your 4 for you. This right here is x to what power? 1/3. Everyone agree? So using this formula, this will be -4 times 1 over, go ahead. 1/3 plus 1, x to the 1/3 plus 1. Okay. Are we done with that middle one? Think so, right? Plus, now how are you going to handle this one? You have to bring that up, and you have to rewrite this as x to the -2. And then you can use the formula, all right? Why can't you do the antiderivative of the top and bottom separately? Like, why can't you do this? Why can't you say that the antiderivative of this is x, because that's the antiderivative of 1, and then the antiderivative of that, you can use the rule, it's 1/3 x cubed. Why do you think that won't work? Because if you took the derivative of this, you'd have to do like a quotient rule, and it's not going to spit that out, I promise. So just like in derivatives, if you have a ratio, you can't do the derivative of top and bottom separately. You have to do the quotient rule. With the antiderivatives, same thing. So we have to get that written as a power. I'll let you continue here. This is no good. So I'm going to have him squeeze it in here. It's going to be 1 over what, Jordan? Negative 2 plus 1. X to the negative 2 plus 1. One more thing. Plus c. All right. There we go. Any questions on that? That's just the mechanics of the formula. Now you got to clean all those fractions up, right? So you should get real comfortable adding 1 to fractions because it's going to happen all the time now. So this will become 3 times 1 over, this is a half plus 1, which is 3 over 2. Then x to the, well, that's also 3 over 2. Minus 4 times 1 over 4 thirds. I'm going to write it over here. 3 times 1 over 3 halves, x to the 3 halves, minus 4 times 1 over 4 thirds, x to the 4 thirds. Where am I at? Here? Okay, so now this one is going to be plus 1 over negative 1, x to the negative 1 plus c. Yeah, let me get rid of that. All right, a little more cleaning up to do here, and we'll be done. So what happens here? 1 over a fraction, this is the reciprocal. So this is really 2 thirds, right? And what's 3 times 2 thirds? 2. So this should just be 2. X to the 3 halves. And then when we flip this one, this will become 3 fourths, and then times 4. So just minus 3x to the 4 thirds. And then this one is just negative 1, and then x to the negative 1. Yeah, we could write minus 1 over x, and then plus c. There we go. Now, how do we know we're right? We can take the derivative of that, right? If we take derivative of that, we better get this. Yes?
What happened to the x to the negative 1 power?
X to the negative 1 is 1 over x.
Oh, you just dropped it.
So I just dropped it. Okay. Let's do another one. I think on this one, I might let you do this one. I'll leave that up there. So how about this? 3x plus 4 cube root of x squared minus x cubed over the square root of x. So before you get yourself too deep into this, can we use this rule straight away on this problem?
No.
Why not?
You have to split it up.
What do you mean split it up?
You have to split them into individual things, terms, so it'd be 3x over the square root of x, 4 cubed root of the square root of, cubed root
Gotcha,
of x
yeah,
squared
gotcha.
over-
Yeah. So this is very important. You cannot do these individually. For the same reason I just explained, we have a quotient here. When we have a quotient, doing an antiderivative is going to be just as complicated as taking a derivative was. We haven't even talked about how we do that yet. The only thing we can deal with right now is when we have x to a power by itself, all right? And so the idea that's being suggested is since we have a single term in the denominator, right? A single term here, we should be able to split this into 3 fractions. This over this, plus this over this, minus this over this. So why don't you take a minute to split it up, clean them up, and then apply the rule. And I'll see how much of that you can get done in the next 3 minutes. Maybe 4. Mm-hmm.
And then convert it to, whatever, 1/3, would you do 2 minus 1/3? Or 2/3?
No, that's, so other students might need this also. Remember that if you have the mth root of x to the nth power, that this is the same as x raised to the n over m. There you go. So whatever the root is goes in the denominator, whatever the power is goes in the numerator. Power to numerator, root to denominator. You guys good? Can I just see your notation? You've obviously done this before, so just curious to see how. No, just more of like how you're writing it. So you're doing that over that. That's fine. Just, yeah, okay. That's
I
good.
just kind of had it as like that.
Yeah, so y'all are comfortable to the point where you always know that the number up front is just always going to be the reciprocal of the power, right? So that's just going to start becoming automatic. Yeah, okay, good. Doing okay? Are you done?
I don't know.
Check it. Take the derivative, right? So bring your negative 1/2 out. Oh, wait, you haven't done the antiderivative yet.
No.
All you've
I
done,
just-
yeah, so leave this little f, little f.
Of the-
All you've done is rewritten little f, right?
So that was right, like I'm just subtracting the
Mm-hmm.
power.
Yep. 1 take away 1/2. So this one should be 1 take away 1/2. So that should be positive 1/2 on the power. Right? And then the next one,
It's
2/3 take away 1/2. Yeah. And then the next one is 3 take away 1/2. So yeah. Now you're at the step of the formula. Yep. Doing okay here? Questions? Yes.
For this one, it would be x squared to the 1/2, right? Or no?
I would write it using that formula right there. So
Oh.
write it as x to the 2/3, which is the same thing, but if you're going to use the rule, you need it to be a power. Yeah. Good here? Questions? Yeah. You're good? Okay. What do you got? I'll come back to you.
I just want to double check here. If we're taking this here, we do this power minus this power.
Other way around.
Or sorry, this power minus
Yes.
this power, right?
1 minus 1/2, 2/3 minus 1/2,
So this is
3 minus 1/2. Yeah, yeah. So, yep. Okay, so you're good? Broke it up. Let's see. Let's do something here. Do you mind if I write yours down up here?
Yeah, it's fine.
Can you feel good about it?
Yeah.
Let's see. I'm gonna put it up here and see if we have any agreements or disagreements. 3/2. Is that minus 2/7? 7/2 plus c. I have no idea if this is right. Anyone else?
Yeah, I got a little different.
You're a little different? You're a little different? Okay. So maybe y'all can talk. Since y'all got different answers, maybe y'all can verify and figure out what is different. Have y'all got it yet? Have you got yours yet? They might be able to help if you're stuck. X is 2.5. Yeah, I'll leave that.
Yeah, I think mine is wrong.
You see it though?
Yeah,
You see
yeah,
it though?
yeah.
Okay. Okay. See if everyone agrees at least with the conversion from here to here. So splitting it into 3 terms, rewriting everything as x to powers, and then subtracting powers. Everyone should be at that step right there. Any questions on that? Yes? You think you got it? Okay. Do you want to just tell me what it is?
Yeah, 2x to the 3 halves
2x to the 3 halves
plus
plus 4
24 over 7
over 7.
24 over 7.
24 over 7.
times x to the 7/6
7/6.
minus 2 sevenths x to the 7 halves.
Okay. Plus c. Were we all agreement on this or not?
No, that's plus, plus.
What is it? Plus what?
Plus 4.
Middle term
2 over
is
2.
positive.
Plus 2 over 2.
Wait a minute.
Plus 4x.
Oh, it was plus here.
Yeah.
Oh, shit, yeah. Plus there,
Yeah.
and that's plus. Okay, yeah. Was that the only issue? I don't know why I put minus there. It's weird.
That last term should be 10 sevenths.
No.
We had 2 7.
No,
Because
it's
it should be like the denominator.
So doing this right here, the antiderivative of the power rule is 1 over n plus 1 x to the n plus 1. That's all right. Okay, can we appreciate the little nuances within here? You got to get all your arithmetic correct, right? And then we could always check it by taking the derivative, right? 3 halves comes out, we subtract 1 from this, we better get that first term right here. And then same thing here, get that, same thing here, get that. All right. So, where do you think you get good at this? In practicing, right? Homework. But the thing about this class, and maybe you've heard this, hopefully I've illustrated this enough, is that by the next time we meet, you all need to be like really good at that. Okay? Like to the point where you're not even really needing to do this step as much as you're just doing it mentally. You already know that that's going to wind up being 2 sevenths. And the only way to get good at that is practice, practice, practice. And you start getting good with it. All right? Okay. How about this one? Well, you know what? We're not ready for that. I'll hold off on that. See if I've taken care of everything I want here with the hyperbolics. Yeah. So here are some examples. I think the first two there are very much like what we just did, right? You could just convert these to powers, use your power rule. What about this last piece right here? This example right there. How would I rewrite that? Yeah, it's really x to the 1 times x to the half, which is x to the what? 3 halves. You add them together, right? So just make sure you understand that's what that would become. This one right here is very much like the one we just did, right? You'd split it up. How about this? How about part C? What would the general antiderivative of this be? So you can do them, there's a plus sign here, right? So you can do them separately. So what's the antiderivative of sine of x? Negative cosine or cosine? What is it? It's got to be negative cosine because what's the derivative of cosine of x? Negative sine, so you need it to be positive sine, right? So, and then, this one right here. You need to know the derivative of what is this? So secant x. And then plus c. So that part C relies on your knowledge of the derivatives of the trig functions. Okay, what about D? I'm real curious to see what you would do on D. Can you all read it okay? I heard split it apart. What else? Anyone else have any ideas? Put it to the -1, inverse tangent. Yes?
I know, but you don't know something.
Well, what are you suggesting?
I know how to do it.
Okay, so what would it?
No, I've done it.
Okay, well then how would you do it?
Long division.
You would do long division, so that might be a way we can go about it too. There's actually multiple ways to do this one. So how is this problem different than this one? A single term here, and here we have two terms, right? So we can split it still, but it would turn out being, what, 2 over 1 plus x squared plus x squared over 1 plus x squared, right? That's the best we could do to split it. You all agree? Now you have to figure out, do you know the antiderivative of these? So do you know the antiderivative of this? Yes? Kind of? Yeah? What is it? So the antiderivative of this, you have to recognize that this, right, is 2 times 1 over 1 plus x squared. And that's the one that I told you need to remember is very important, right? So since this is actually this, we know that the antiderivative of that is 2 arctangent of x. Right? That would be the antiderivative of this one. Everyone agree? How about that one?
Tangent. So isn't that x squared times arctangent?
Oops. Well, let's see. Is it? I mean, yes, it is. This one right here, I agree, is x squared times 1 over 1 plus x squared, right? That's what that is? That is that. And I do agree that the antiderivative of that is arctangent. But the problem is you have a product here, right? Like this is being multiplied. So, I mean, maybe if life were good, maybe you would think it's like this. Maybe.
It can't be x squared times arctangent of x.
Okay, so let me say, or maybe it's x squared times arctangent of x.
Like you did the first one.
Yeah, okay, so the way I did this one, it was a constant, right? So I pulled the constant out. And the reason why that's okay is because the derivative, when you have a constant in front, just comes for the ride, right? But when you pull a variable out, what's different? When you take the derivative, what would happen? So if you think it's this, you need to take the derivative of that and get back this. And why won't that work? You're going to have that product, right? You're going to have product rule here. And so you're going to get 2x times this plus the derivative of this times this, and it's not going to turn out to be that. Do y'all see what I did here? What did I do? This was suggested. We understand this isn't going to work. Do you see what I did? It's not right, but do you see what I did? I just did antiderivative of this, antiderivative of that, and that's wrong also because, again, if I try product rule on that, take the derivative, I'm not going to get that, right? So what then? That's what the next couple of weeks are about, is, how do we deal with something like this, right? It's not easy. Now, there is a way around this. We can do it, and it was long division is the way we can get this. So you ready to see that, just so you can see it? We've got this one, right? This is check. We got it? So let's do this, and let's rewrite it like this. Let's do long division. I'm going to write that backwards. Okay, so when you take x squared and divide it by x squared plus 1, what goes here? 1, right? So you say, okay, what turns x squared into x squared? Just 1. So you go 1, multiply, you get x squared plus 1. Then you come through and you subtract this, right? Subtract, subtract. So what would you have here as your remainder? -1, right? And so x squared cannot go into that. So this is your remainder. So you put plus your remainder over your divisor. So that's your long division, right?
Where did the -1 come from?
When we do long division, when you do this times this, put it here, and then you subtract that row. So all the signs change. Right?
I haven't done long division since
All right, so if you haven't done long division in a long time, go get brushed up on it, because we're going to need it, all right? Yeah. I mean, but you just think about it this way. Like if you have 15 divided by 7, how do you do that? 2 here, right? 14, then what do you do on the next step?
Oh, okay.
You subtract, right? Same thing. So we do, we did, that goes, to turn this into this, we hit it with a 1. 1 hits those, come through, subtract, and then we get the negative 1. All right, so what we're saying here is that this expression right here is the same as 1 plus negative 1 over x squared plus 1. Right, that's what we're saying? And now, can you find the antiderivative of this? Yes, because what's the antiderivative of that by itself? Just x, so plus x. And what's the antiderivative of this? Negative tangent inverse. Why negative? Yeah, because that negative 1, just pull it out, and then it's 1 over 1 plus x squared again. Now, we could actually clean this up. I need my plus c. We could clean that up, couldn't we? Because we have this and this. These are like terms. So it's just arctangent. 2 of them take away 1 of them, right? So arctangent of x plus c. There we go. All right. So we're just barely putting the tips of our toes in the water here, all right, in terms of antiderivatives. This is the very beginning of it. And we're going to talk about one more thing, and then we're going to move to our first real technique of integration, or finding antiderivatives. But we got to finish this section off, and this section talks about rectilinear motion, or rectilinear motion. Basically, motion in a straight line. So if you have an object moving in a straight line, that's what we're talking about. So remember from Cal 1 that if you have the position of an object moving in a straight line and that it's given by some function, in this case we'll call it s is the position, is some function of time. So that tells you where an object is at every point in time, all right? Then the derivative of that position function is the velocity function. This is a Cal 1 thing. And then the derivative of the velocity function is the acceleration function. Does that seem familiar from Cal 1? Okay, that's what you should have seen. So if you haven't seen that, maybe you come by my office and we can talk about it. But here I'm assuming you know that. Therefore, what if we go backwards? What if someone gives us an acceleration function and we're asked to go back and recover the velocity function? What will we have to do? Take the antiderivative, or find the antiderivative of the acceleration function. And that would give us a velocity function. And then, if we want to get the position function from the velocity, we'd have to go back again, wouldn't we? Take the antiderivative. But what's the problem with that, though? Like if I give you an acceleration function and ask you to find the velocity, what's wrong, what's going to be bad when you do that antiderivative? You have a plus c, right? So you'd only be able, if I give you acceleration, you're only going to be able to give me the velocity within some family of curves, right? Some family of functions. You're not necessarily sure exactly which one it is. And then when you go backwards again to your position, it's another kind of unknown family. So it's a little more problematic than in Cal 1 when we move this way, derivative. When you take derivative of a function, there's only one answer. Antiderivative, there's a family. So is there a way we can get around this? Well, there is. We need someone to provide us with what are called initial conditions or conditions. So look at this example. If the acceleration of an object that is moving in a straight line is given to you by a of t is 24t minus 6, and they're telling you that s of 1 is 7 and v of 2 is 41, we want to find the position function of the object, and then we want to find s of 2. All right, so let me try and explain what this is all saying. Right now, all we're saying is that if somebody gives me the time, we know the acceleration of an object, right? You just tell me time, I'll tell you the acceleration. That's all we have. And from that information and these two pieces of information, I should be able to recover the position where the function was at every point in time. All right? What are these two pieces of information giving you? So what is this giving you?
Speed and velocity. Speed.
No, S is the what? Position, V is the velocity. So this is saying, this is telling you that the position of the object after, let's say, 1 second or something is 7 meters or miles. We don't know the units. It's not given to us. And then it's given, what's that?
Who's giving us a point, right?
It's a point, basically. Yep. So this one is giving us a point off of the velocity curve. So let me try and show this to you visually. We have position function, we have velocity function, we have acceleration function, right? We know this one, right? We know this one. It's a linear function, isn't it? This is your a of t equals 24t minus 6. If I want to go back to velocity, what type of function am I going to get? If this is linear, when I go backwards, what am I going to get? Antiderivative. So the antiderivative of a linear function should be a parabolic, shouldn't it? Agree? Because the power is going to come up on these. So the antiderivative of this gives me a family of functions, of parabolas in here, right? This piece of information right there nails down which one it is in that family. Only one of those curves passes through the point 241. Out to up 41, boom, it's that one. Now, we know it, right? Do you all see that visually, what's happening? So from here to here, we get a family. This piece of information gives us the exact parabola. Now, we do it again. There's our parabola. We go backwards. If we go backwards, what type of function are we going to get here? Cubic, right? Third degree. So that'll look like something, whatever it is. And it's a family, isn't it? And this piece of information is going to nail down which of these it is. And then we will know the position of the object at every point in time. Yay or nay? Some glossy looks on your faces. All right, let's do it. This is me trying to visually explain what we're doing. Now let's actually do it. So our acceleration function is 24t minus 6. So our velocity function would be, Max, are you ready for this or no? Where's Max? Okay, are you feeling okay or no? Okay, so antiderivative of 24t is what we're looking for. Okay, 24 comes down.
T plus 1.
1 over, so the power here is 1, right? So
Yeah, so it'd be 1 over 1 plus 1.
t to the 1 plus 1, right? Okay, I agree. And then minus, what's the antiderivative of 6? 6 x, but here t, right? Because we're using the variable t. And then plus some constant, right? All right, so this is really 1/2, right? Half of 24 is 12. 12t squared minus 6t plus c. Max, that all right?
Yes.
You understand that? Okay. So we have the velocity function within a constant. We've got the family. Now it's time to nail down which one it is. So Corey, where's Corey? Corey, any ideas how we're going to nail that family down?
Definitely plug in.
Yeah, use this, right?